the expert TA assignment that will be due on Wednesday, the day of the test. So you'll have all of that at your fingertips. Okay. Um, Number three, you had options, but none were like just self-evident. Like they weren't just obvious. If you use all 8 seconds, then your displacement is zero. Why would your displacement be zero? That does not seem to make sense, Tyler. You start and stop at the same height. Displacement zero. Okay? Or this is the more popular route is hey, at the highest point, the velocity is zero. Therefore, time up equals time down. So this is 4 seconds. Here's a popular pitfall. Ready? There you go. 8 seconds and final velocity is zero because they think here the ball hit the ground. Is that free fall?
Yes.
When the ball hits the ground?
No.
No. Okay? You see the problem with that. Okay? You're moving really fast at 8 seconds. You have not hit the ground. Okay? Good with that? Number 4. That's kind of crazy, yeah?
Nice.
So if you throw the ball down and you throw it up at the same speed, throw it up at the same speed, it's going to hit the ground with the same speed. Not at the same time. I'm not saying that. What I'm saying is it's going to hit the ground going the same speed. Because if you throw it up here, how fast is it going right here as it's coming back down? Same speed. Just as if you threw it down at that speed. You okay with that? Not at the same time. Okay? Here's something that I want you to appreciate and adopt. Here's my initial, here's my final, even though it goes up and it comes back down. My displacement was still a negative 20 meters. But it went up. It sure did. You could, if you really, really wanted to, would not recommend it. You can subdivide that on the up and then the down. You'll get the right answer, but it's just like 3 times as much work. Okay? All you care about, just like with the fan cart, you can call anywhere along that arc my initial and my final. And it worked out. Okay? You do not need to subdivide that. You can. It's not illegal. You're just wasting a lot of time. You might really like to do physics problems. I don't know. Okay? So we're good with that?
Yeah.
Okay. Number 5 was a doozy. There was copious amounts of work to do. Okay? So, a lot of you had this. Okay? That's where the rocket is when the engine turns off. But check this out. My hand's going to be the engine. This is going to be the rocket. Okay? We're going to start at the ground. After I stopped pushing it, did the rocket stop? No. Why not? Because it has inertia. It's now moving. It wants to keep moving. And now it's in free fall. Okay? So initially, it was not in free fall. There were other forces acting on it besides gravity. Do not put 9.8 there. I told you the acceleration, but anyway. Um, so you've got two phases, two stages, okay? So remember when we were talking about the bear and the tourist? Have multiple objects, and you need multiple, like you need a set of variables and an equation for each object. Okay? Same goes true with multiple stages. Remember the running and the jogging, or like the walking and the jogging. Totally. Okay? We have two different phases. We have the engine on, and then we have the engine off for free fall. The thing that made this more complicated was the free fall part was stacked on top of the engine on parts. So it's kind of like a relay race. So we needed to figure out, okay, we know where the rocket is at this point, but we need some more information for the free fall part. I need to know how fast it's going. So I need to do an additional calculation for the engine on part for like roughly 4 seconds. So it's going roughly 30 meters a second. So you figured out it's going like roughly 120 meters a second. And then that final velocity of this initial part became the initial velocity of the second half. And the final position during the engine on part became the initial position for the engine off, the free fall part. Full on. So, trying to be fully disclosing, I will not give you a problem this extensive on the test. But what I can do, because I feel like there's lots of places you can derail, and that's a lot of like, but what I can do is I can say, hey, you've got this, 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 this. I'll give you things. What do you do after that? How do you handle it? Like, I'm doing a lot of the grunt work. I want to know what's like strategically wise, how do you do the next step? Does that make sense? And that's what you experienced on last test. Okay, what's the average speed? I gave you a whole bunch of stuff. You didn't have to calculate much. You just had to know what you are looking for. Okay? That's what I'm trying to coach, teach is not can you repeat problems, but can you think through, here's what I need to get to where I want to be. Good? Okay? How are you feeling about that? Awesome. Okay. I want you, if I were to toss a ball over a motion detector, motion detector's right here. I'm tossing the ball like this. What does the position versus time graph look like? What does the velocity versus time graph look like? Okay, need to predict. What is that going to look like? Velocity and position versus time graph. Everybody have a hypothesis? Good. Here we go. Ready? Here we go. Good prediction.
Yeah.
Nice. First try. That is so good. All right. So I'm looking at this right here. This is looking real pretty. Look at that. How'd we do? Okay.
Yes.
What on a velocity versus time graph tells us acceleration? Slope. Check this out. Slope, or like y equals mx plus b. Slope, negative 9.5. Pretty close to negative 9.8. With some experimental error. That's reasonable. Cool that. Oh yeah. All right. Next question.
If you do pretty
Have a conversation about this question. Correct answer is C. And what is that value?
Negative
9.8 meters per second squared. We're good at that. If you were tempted to say B decreasing, you're still confusing velocity and acceleration. They're different. The velocity is decreasing. The acceleration remains constant. You're changing your velocity at a constant rate. Next question. Good. This one did not require you to be in physics to know this one. Correct answer is B. The thrown one. Yes?
Yes.
Okay, obviously, you threw it. Okay? This was a warm-up setting the stage for this question here. It's the same scenario, but a different question. Thumbs up when you have an answer. Thumbs up when you have an answer. Which one experienced a greater change? Have a conversation.
C.
I feel a lot of stuff now. That's like like I said, I give that so much review. Sounds like yes, I started varsity in a
What do we say?
C. Because everything that
Good. They both experienced the same acceleration for the same amount of time. Therefore, both of their changes in velocity are going to be identical. Not their final velocity, but their changes. Because they experienced the same rate of change for the same amount of time. Example, drop rock goes from 0 to 10 meters a second in 1 Mississippi. The thrown rock, I'm making this number up, goes from 20 meters a second to 30 meters per second in 1 Mississippi. Both experience the same change in velocity. They're not, the one thrown is definitely going faster, but both experience the same change because they experience the same acceleration for the same amount of time. Good? Huh? Next question. Influence or be influenced by others? Yes. Have a conversation.
until like it doesn't reach its full velocity. Speed. I think it's gonna be speed at half its velocity until it 70 degrees to get to weight velocity. And then so velocity is pretty so I was like I didn't see that. So
Okay, what do you say?
C. Everyone just unanimously goes for the obvious answer.
All right. Correct answer. So they both like it's experiencing a constant acceleration, meaning that your velocity is changing at a constant rate. You could solve it mathematically with that kinematic equation. If you're like, I don't know. Okay. Graphically, your velocity versus time graph, like visualize what that's going to look like for this dropped rock. Velocity versus time is going to look like that. How'd you do? It's going in the negative direction, starts at rest, speeds up at a constant rate. Okay, so this would represent 30 meters per second. At half the time, you're at half the change. Okay. Because you change at a constant rate, because you have half the time, you have changed at half the rate or half the amount. Okay. Next question. Same scenario, different question. Okay, think to yourself. Do not influence or be influenced. Think. The previous answer was A, 15 meters per second. This question is asking about looking at your position. Tight, fast, anticipation, talk.
This one is C.
And talking.
Yeah. What's my God? This one
What do you think?
It's either A or C.
How far will that drop?
What do you guys think?
We're doing some speed. Looking at that list right there.
You know, looking at this.
Actually, you're
Right
right.
answer is. Okay. You could solve it if you wanted to, but your position versus time graph, visualize that. Everybody got something? Start away and do something like that. Okay. So that's 3 seconds, half the time. You've only fallen just a little bit. So if it asks for a displacement, it would be less than 22.5. But because it asks for position, asks for your height. How? Oh no, it didn't. It asked for how far. So less than. It's less than 22 meters. Good with that? Last question.
I don't know.
You back?
Hang tight on the conversations. Have a conversation now about this question.
When the work and the results, I'm doing that. You were staring at me for 30 minutes.
No, do it. Do it what?
Is he a
Either.
Wait, so
Go ahead.
huh?
The power of friendship. Oh, he has a new word. Yes, I thought you
On
said
the calendar. I was thinking.
no.
Okay, what do you say? This is a hard question. Okay, at half the distance. At half the distance. You're way more than half the time. Is everybody okay with that? So at more than half the time, you're going faster than half the speed. More, at half the distance, that's more than half the time, therefore you're going faster than half the speed. You okay with that? Okay, B.
Yes.
All right, demonstration for you. Okay. If you have issues with strobe lights, close your eyes and pretend you're in a happy place. All right, here we go. We've used strobe lights in science way before they used them in parties. They still use them in parties? No. Oh man, you should try it. It's pretty cool. Okay, so does everybody see the fan? Is the fan still spinning? Why does it look like it's stationary? Oh, look, it's going backwards. Oh, it's waving. Okay, quick explanation. As the fan goes around, it's going flash, 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 flash. So if you know the rate at which it's flashing, you know the rate it's spinning. You cool with that? Yeah. Okay. So we're going to use this same idea to freeze something in free fall. Okay, I'm going to drip some milk. Okay. If you can't see it, move so you can. We're dripping up right now. See if we can get it dripped down. Okay. Here's what I want you to see. Right here, you see the gap distance? About this. As it goes down, you got a gap distance of this. Why is the gap distance bigger at the bottom? It's getting faster. Dripping up. Slowly dripping down. You see that? Cool with that? Okay, if you can't see it, move so you can. I mean, it's a cool demonstration. It's one of my favorites. Everybody good with that? Let her rip. Cool. Let her drain all the way out there. If you need to go to the bathroom, you can go to the bathroom. I don't know how it's gonna look on the video, but